Swayam Prabha. Digital India. Educated India.
So we continue with sequence components today. We have looked at the sequence transformation, its utility for protection engineers, the linearity of the transformations. So today we will look at how we use this for modeling of network components, and then go on to use it for fault calculations. So we will first look at what happens when the network is balanced. The greatest utility of the sequence transformation is when the networks are balanced. Okay, when it is unbalanced, then you don't get the decoupling, as we shall see. Assume that you have a transmission line, a three-phase transmission line. I am drawing three separate wires for the three phases, say A dash, B dash, and C dash, and the voltage drop across the transmission line is given by delta V. So, across the A phase it is delta VA, across the B phase delta VB, and across the C phase it is delta VC, and the respective currents are IA, IB, and IC. Also, let the self impedance of each phase be ZS, and the mutual impedance between phases, between A and B, B and C and A, BZM. What this implies is that the transmission line is transposed and the mutual impedances are the same between each phase. So now if we write this in terms of the phase domain, it will look like delta VA, delta VB, delta VC is equal to ZS, 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 IA, IB, IC, and the off diagonal elements are the ZMs, which are the mutual impedances. Okay. Now, if we were to apply our symmetrical component transformation here, to get it in terms of the symmetrical components, we will get it as T, which our T matrix is what we discussed last time, 1 1 1, 1 A square A, 1 A square. So, T into delta VA, delta VB, delta VC is equal to ZS, ZM, 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 ZS, ZM, and T into IA, IB, IC, which will give us T into VA0, VA1, VA2, and similarly this will be IA0, IA1, IA2, and this will give us, if we pre-multiply by T inverse on both sides, Zm, Zm, Zs and into T into IA0, IA1, IA2. Okay. Now T inverse into this Z matrix into T will, if you solve this, it will diagonalize the Z matrix, and you will get, you should do this for yourself and see. Zs plus 2 Zm, this is 2, 0, 0, 0 Zs minus Zm, 0, 0, 0 Zs minus Zm into IA0, IA1 and IA2. So, these three elements we will denote as Z0 equal to Zs plus 2 Zm, Z1 equal to Zs minus Zm, and Z2 equal to Zs minus Zm. Z1 is equal to Z2, which is these are the 0 sequence, positive sequence and negative sequence impedances, and as I was saying, Z1 equal to Z2, which is true of any static equipment. Okay, so we can write this, we can rewrite rather this equation as delta VA0 So, if you notice here, we get delta VA0 is equal to Z0 IA0, delta VA1 is equal to Z1 IA1, and delta VA2 is equal to Z2 IA2. The thing to be noticed here is that you get a nice decoupling between the sequence networks. So, even though in the phase domain the phases were coupled, here in the sequence domain the sequence networks are decoupled. So, they can be analyzed independently, and then if you want the answers back in the phase domain, you will have to do an inverse transformation. So, this is a nice and elegant way of looking at network analytics like faults, fault calculations, etc., which we will see in today's lecture and the next lecture also. So, going back to our slide set, this is what we get, which is what we just derived. Okay, so we will look at a few advantages of sequence components and then go on to modeling of other network components. So, as we saw, the biggest advantage is when the network is balanced and it provides a decoupling. It can be applied whenever the network is balanced, but the loads can be balanced or unbalanced. Okay. If the network itself is unbalanced, then there is no big advantage in using the sequence component transformation. Also, things like earth fault detection, etc., can be implemented using zero sequence currents. Okay, so this is a useful technique that we learn about. We will see fault calculations a bit later. First, we will see modeling of sequence components. We will also have a look at a few problems in the next class, so that our concepts of sequence components are a bit more clear. So, we saw per unit calculation and its advantages in the last lecture itself. So, we will quickly move on to modeling of transmission lines. This is the first network element that we consider. We actually just derived this this expression. We will quickly go through it we revise our concept also. Now, as you can see here, and as we just derived, the positive and negative sequence impedances are equal. Now, this is true of any static equipment like transformers or transmission lines. It is, however, not true for rotating equipment, because the rotor obviously cannot rotate in the positive and the negative direction at the same time. So, for rotating equipment, Z1 will not be equal to Z2. However, for static equipment, Z1 will be equal to Z2. Also, the thing to note is that for transmission lines, also for transformers, as we will see later, is that the zero sequence impedance is not equal to either Z1 or Z2. This is because the return path for the zero sequence currents is through the ground. For positive and negative sequence, IA plus IB plus IC is equal to 0. So, nothing, even if there is some ground resistance or ground impedance present, since the current is 0, the voltage drop will be 0. So, it does not matter whether whatever is the ground resistance or impedance. Here, in case of zero sequence currents, some part of the current will return through the ground, some part will be returning through the earth wire, etc. So, the zero sequence impedance of the transmission line is not equal to the positive sequence impedance, and it is usually taken, if you do not know the exact parameters, etc., it is usually taken to be around 3 to 5 times or 3 to 6 times that of the positive sequence impedance. Now, also because of these, because of the variable nature of the soil resistance, etc., it is not very easy to determine the zero sequence parameters a priori in terms of calculations, etc. It has to be determined using tests. So, and that is why the design values may not be very accurate. They can be off by 10-15% also, which is not the case with positive and negative sequence impedances. The design values can be fairly accurate. So, one more aspect of transmission lines is mutually coupled lines. This is not something that we consider in load flow or power flow studies, etc., but however, it becomes important in terms of short circuit studies. Why, we will see shortly. Okay. Now, consider these are two circuits, A1, B1, C1 is circuit 1 of the transmission line. A2, B2, C2 are 3 phases of the circuit 2 of the transmission line. So, there are 2 circuits strung on the same tower, and this, which is very common, you have double circuit transmission lines, very commonly you can observe them whenever you see transmission lines. Here, for the sake of convenience, we are taking that the circuit 2 is not energized, that is the currents flowing in that circuit are 0. Now, due to the currents flowing in circuit 1, what is the flux linking the conductor in circuit 2? So, we will start with the A2 or the phase A of circuit 2, and then we can extend it to the other conductors. Now, if you look at, if you start with Ampere circuital law, then the circular integral H dl is equal to the net current enclosed in that path. If you see the path which is shown by the dotted lines, then for the positive and negative sequence currents, IA plus IB plus IC is equal to 0. So, the net flux, positive and negative sequence flux linking the conductor A0 is 0. However, for the zero sequence network, there will be some flux linking which is dependent on the current I0, because the net current here is not 0, it is the zero sequence current in the circuit 1. So, this if you see that the inductance will be N phi by I. So, there will be some zero sequence mutual inductance, and in turn there will be some mutual zero sequence impedance also. So, the thing to note is that there will be mutual impedance, but it will exist only in the in the zero sequence component. Okay. So, the earlier modeling of the transmission line we extend to the circuit 2 also. This IA1, IB1, IC1 are the currents from circuit 1, and IA2, IB2, IC2 are the currents in circuit 2. And this is another assumption, that all the mutuals are equal to alpha or J alpha. Okay. So, if we apply the zero sequence, if we apply the sequence transformation, our T inverse ZT for both the matrices here, for this ZS, ZM, Zm matrix, and also the alpha matrix, which is the mutuals of circuit 2, then we will get the matrix as shown here. This is the earlier one that we got, Z1, Z0, Z1, Z2, and this here Z0, Z1, Z2, and here only for the zero sequence current there will be a zero sequence mutual impedance present, which is 3 alpha. So, mathematically also we have proven what we saw analytically earlier, that the mutual coupling exists only in the zero sequence network. So, that is why whenever you do say power flow studies, you do not consider this zero sequence coupling. Only when you do short circuit, that this will become important. So, one more aspect that has to be noted is that for positive and negative sequence, as we mentioned earlier, the current flowing through the ground is 0. So, the ground can be considered as a true zero potential surface. There is no voltage drop associated there, but the same cannot be considered for the zero sequence circuits. So, to get a true zero or equipotential surface at the ground, we lump the zero sequence impedance with the actually the zero sequence ground impedance with the zero sequence impedance of the equipment. We will see when we see generator modeling. Okay. We will move on to the transformer model now, that is the sequence modeling of the transformer. Now, there are two aspects to be noted in the sequence modeling of transformers. The sequence connection depends, or the sequence impedances rather depend on the transformer type, construction type, that is whether it is a core type transformer or a shell type transformer, and also the connections, whether it is a star delta, delta star. We will see that shortly. So, now first we will look at the core type transformer. Here phi A plus phi B plus phi C is equal to 0, and so for zero sequence impedance, phi A, phi B, phi so for zero sequence impedance it will be 0. So, since the flux is 0, there is no zero sequence inductance associated with this. However, practically it is not 0. There will be some path which exists for the zero sequence flux through the tank and some common metallic elements, and that is why there will be some leakage, and this zero sequence there will be some zero sequence flux which is very low compared to the positive and negative sequence fluxes, and hence there will be the zero sequence inductance will be much lower than the positive and negative sequence inductance, close to 0, but not exactly 0. And one more point to be noted is that since the saturation is not considered, we are not considering only magnetizing impedance here, we are considering only the leakage impedance when we do the sequence modeling of a transformer. Now, the other type of transformer is the shell type transformer. Again here the positive and negative, the treatment is similar to that of the core type transformer. Here the difference is that there is a path for the zero sequence flux through the outer limbs, and hence there is a low reluctance to the zero sequence flux, and hence the flux is high. So, the impedance, zero sequence impedance will also be high, at times considered equal to the positive and negative sequence impedances also. If the exact value is not given, you can consider that. Now, for a single phase transformer, rather a bank of single phase transformers connected together, the positive, negative and zero sequence connections, or rather the positive, negative and zero sequence impedances are the same. So, positive sequence equal to negative sequence equal to zero sequence impedance, if it is a bank of 3 single phase transformers connected together. Okay. So, one more factor to be noted now, which is considering the connection. Now, we are not considering the construction, but rather the connection of the 3 phases. So, if they are connected in delta, then you can see that the zero sequence currents can, because they are in phase, they can flow in the limbs of the delta. However, externally, if you apply the KCL at the nodes, you will see that externally in the phases which are connected to the delta, or the lines that are connected to the delta, the zero sequence currents are 0. So, you have to keep this in mind when you look at zero sequence connections of delta connected transformers. Now, we will have a quick look at how the connections vary when the vector groups are different. It is there on the slide, but we will quickly have a look at some of them on the okay. So, now consider that we have a star grounded, and that is the positive, that is the high voltage side, and the low voltage side is delta connected. Okay. So, for positive and negative sequence, and consider that ZT is the leakage impedance of the transformer, and this is the reference bus. Either reference bus is usually denoted N. So, either N1 or N2 for positive sequence and negative sequence respectively. So, for this transformer, in fact, for all transformers, the positive and negative sequence will be equal to the leakage impedance of the transformer. So, it is ZT. However, zero sequence, in this case we saw that no zero sequence currents can flow in the connections to the delta. So, it will be open at this point here. However, because the zero sequence current can flow in the limbs of the delta here, I0 can flow here, there will be equivalent zero sequence currents flowing in the star side, okay, provided it is grounded, of course. So, that is why this connection here is through. However, note that it is open here, and the delta will isolate everything that is upstream or downstream of that transformer. Okay. Similarly, if this is grounded through a grounding impedance or a grounding resistance, which is done to limit the single phase fault current, then as we said, this positive and negative sequence will be the same. However, for zero sequence, we will get an additional, this is ZT, we will get an additional 3Zn here. So, this will also limit the zero sequence current. Okay. This will still remain open. If it is delta and delta, this is H, H means the high voltage side, L is the low voltage side. Again, this is the same for whatever connection that we take, positive and negative sequence connections will be the same irrespective of the vector group. However, here there will be a change in the zero sequence. So note that here it is open at 2 points. Okay, this is because no currents can flow in the lines connected to the delta. If it is a star grounded transformer, let's the positive and negative sequence will be the same again as we said, and in this case the negative the zero sequence will also look similar to the positive and negative sequence component. This is either N1 or N2 and this is N0. Okay. However, if there is a grounding impedance in one or both, let us take the case of both. This is H and L, then this of course remains the same, sorry, N1, 2, this is ZT, and this will be the zero sequence, there will be a 3, say this is Z N H and Z N L. So, three Z N H, Z T, 3 Z N L. If only one is present, then if this is not present, then this will not be present. Okay. So, we will just complete this. Say you have a star grounded and a star ungrounded, then as we said, this is H and L, please remember that. Then this will be open. Okay. If I were to earth this neutral, then there will be this will be closed. Okay. If just one more case. So, since it is a delta, it will be open from here obviously, but since this star is ungrounded, it will be open from here also. Okay, so, it is open at 2 points. If this star were to be grounded, then this can be closed. Okay. So, that completes our two winding transformer connections. How we use them for fault calculations, we will see either in this lecture or if time permits, or we will see that in the next lecture. Now, we will have a quick look at 3 winding transformers. Now, in 3 winding transformer, there are 3 windings: the high voltage, the medium voltage and the low voltage winding. And depending on the type of connection, the sequence component also will change. The thing to remember here is that usually you will be given the impedances not as ZH, ZM, ZL, which you will need to for the sequence component modeling, but you will be given them as say ZM, ZHL, that is the ZHM and ZML. Okay. So, the the definitions are the same. The that is the leakage impedance, which is calculated in the similar way as a two winding transformer, only that the third winding is left open circuited. So, you will be given some values here like this. Now, you have to find ZH, Zm and ZL from the above three values here. So, you do that as follows: ZH is equal to half ZHL plus ZHM minus ZML. So, it is some sort of it is not exactly a star delta transformation, but you can consider it as some sort of Zm we will take. That is a medium voltage winding, that is given by ZHM plus ZML minus ZHL. Similarly, ZL is given by half ZHL plus ZML minus ZHM. Okay. And for the two winding transformer, you had the positive and negative sequence impedances representation by the leakage impedance like this. Say this was N1 or N2. Here this will be like this. Okay. Say this is the reference bus, then this will be ZH, ZL, and Zm. Okay. So, this is the reference bus N1 or N2. Now, depending on the connections, the zero sequence connections will be different, or the zero sequence network connections will be different. So, now consider we will quickly consider 2 or 3, so that you get an idea, and then we will move on to generators. So, this H high voltage winding, consider it as a star grounded through a grounding impedance Zn, and consider that the other two windings are the medium voltage winding and the low voltage winding are deltas. So, as we said, the positive and negative sequence impedance connections will be the same. They will be so this will be ZH, ZL, Zm. Zero sequence I will draw a little below. So, here since the two windings are delta, we have to take into account that there will be no zero sequence current in the line. So, similar to that of a two winding transformer, only that there are three Zn. This will be open, and this will also be closed. Oh, I am sorry, there has to be a so 3 Zn, this will be Zh, this will be Zl, and this will be Zm. Okay. You notice that these two the circuit is open at these 2 points. Now, if there was say one of the winding of the two was again a star winding with or without a grounding impedance, say this is ZNH, say H, and say M was also a star NH, ZNM, and this is a delta. So the positive and negative sequence are the same as this. I am not drawing that again in interest of time, but the zero sequence impedance in this case will be network, rather zero sequence network impedance will be like this. Okay, so this is 3ZNH, this is ZH, this is ZM, this is 3ZNM, this is ZL, and this point is open. So you can make out that whenever there is a delta connection, a path to the ground will exist, but in the lines no zero sequence current can flow, so it has to be open. Whenever there are star connections with or without grounding impedances, you will configure the network accordingly. Now say if this star, will quickly take one more case before we say this one was ungrounded, okay. Then what you do is this will also be open. So there will be one more open point here, okay. So you configure the zero sequence networks accordingly, okay. So now we will have a look at this we saw. Okay. So we will see the zero sequence and of course the positive and negative sequence modeling also of the synchronous generator. The impedances in the circuit will be determined by the what are the time durations that we are looking at. If we are looking at the first cycle after the fault occurs, then we are looking at the subtransient reactance. If in about 100 milliseconds or so, that is around 5 cycles, this has now increased to the transient reactance xt dash, and maybe around 500 milliseconds to 2 seconds or so, it is the saturated reactance or the synchronous reactance. Okay. So how do you connect these? We will have a look at that before we stop for today. Consider a synchronous, an unloaded synchronous machine. Okay. So this is the phase A. Also positive and negative ending. This is phase A. Phase B, this can be written as EB and this can be written as EC. Okay, so this is IB. This is the IA and IC. Okay, so and we will also take this is connected to the neutral is connected to the ground through a grounding impedance Zn. Okay. So, first we will have a look at the positive sequence, then we will have a look at the negative and zero sequence. No, there will be a generated voltage here first. This is our reference bus, the same as that we saw earlier in the transformer model. Okay. And the equation is VA1 is equal to EA minus Z1 IA1. Okay. Okay. So, now what about negative sequence? Now, if you can imagine, if you excite the stator of a synchronous machine with a negative sequence supply, you will get a rotating magnetic field which rotates in the opposite direction to that of the positive sequence, which is the conventional rotating magnetic field that we consider. This rotates in the opposite direction with the same speed as that of the forward rotating magnetic field. So, this is with reference to the rotor, this is rotating at twice the synchronous speed. Okay. So, this will induce double frequency currents in the rotor, and which will then act to reduce the by Lenz's law, which will then act to reduce the negative sequence flux in the machine. So, the negative sequence impedance is not the same as that of the positive sequence impedance. In fact, it will be lower because of this action of the net reduction in the flux, and it is usually considered to be about 70 to 90% of that of the subtransient reactance. So, X2 will be equal to 0.7 to 0.95 or 0.9 or 0.95 of XD double dash. Similarly, zero sequence currents, as we saw in the last lecture, they cannot create any rotating MMF. We proved it mathematically also. The net flux, the net zero sequence flux at any point in the air gap will be zero. Theoretically, the zero sequence, because the flux is zero, the impedance should also be zero. The inductance, that is N phi by I, should be zero, and the impedance in turn should also be zero. However, that will not happen because your windings are not exactly distributed at 120 degrees. There is some fractional pitching and all that, and and there will be some zero sequence flux as a result of that, and hence it is considered to but it will be very small. So hence it is considered to be around 10% or to 70% of that of the positive sequence impedance. So X0 is equal to 0.1 to 0.7 times that of the positive sequence impedance. Also, if the machine is grounded through Zn, as we saw, then that also has to be considered. We'll quickly see how that looks like. We saw this is the positive sequence. For negative sequence, since there are no negative sequence generated MMFs, there are no negative sequence generated EMFs, the machine will look simply like this. In the positive sequence, you had a positive sequence EMF in each phase. Here you will not have that. You will have only this is how it will look like, and the negative sequence equivalent will look like Z2, VA2, IA2. So, VA2 is equal to minus IA2 Z2. Okay. For the 0 sequence, you will have an additional, if this was, okay, we'll if again there are no 0 sequence generated EMFs, so it will be simply this. However, we have to consider now that there is a Zn here, okay. So, this will now look like 3 Zn plus, this is just for the sake of convenience that we are labeling the 0 sequence impedances of the generator as Zg0, and this will be Ia0 Va0. Okay. So, Va0 is minus Ia0 Z0, Z0 in turn is equal to 3 Zn plus Z0. So, when you consider impedance in the neutral or grounding impedance, it will manifest as 3 Zn in the 0 sequence network. That is because you have 3 I0, that which is Ia0 plus Ib0 plus Ic0, which are equal, flowing through the neutral. So, and you want to depict it in terms of I0 only. So, the equivalent drop, which is 3 I0 Zn, is then shown as I0 into a 3 Zn drop. So, that is why this 3 Zn appears in the 0 sequence network. Okay. So, we will stop here and continue next time with the other network components.